Hello and welcome to the module Transfer Functions and MOSFETs. In this module we're going to be looking at our speed control circuitry as a system. We're going to finally add a reference voltage which we'll use to control our motor speed in a closed loop system. Now we'd like to simplify how we represent this system a little bit by using models for each of these elements. We'd like it to be simple enough that it's easy to draw an equation which relates our reference voltage directly to our motor speed. Now if we just list what we've done so far, you can see we have our motor driver over here and our speed sensor circuit down here. And our motor driver takes VO as an input, which controls the current through our motor, generates some omega, or some speed on our motor, which our speed sensor then translates into this Vs voltage. Now you can imagine doing open loop control on this system where we simply measure Vs, determine whether our motor is going fast enough or too slow, and based on that increase or decrease VO. Now this type of system has one major issue, which is that the same VO is not always going to relate to the same omega. If we have different torques on our motor, for example if our robot's going up a hill or down a ramp or something, it can take more or less current in order to achieve the same omega. Meaning that if we simply measure Vs once, determine the correct VO, and then try and use that at all conditions to get some motor speed, it's not going to work. In this system we'll have to continually be measuring Vs and modifying VO in order to maintain a constant omega. And we don't want to have to do that. It'll make it a lot of work in order to maintain a constant motor speed. What we'd like to do is add a reference voltage, Vref. We can simply set Vref to the value we want, corresponding to the motor speed we want. And then we'll use some sort of a feedback controller, which is going to take the error between our reference voltage and our actual voltage. So it's going to look at the difference between where we want to be, which is this Vref, and where the motor actually is, which is this Vf. And we want that feedback controller, or that compensator, to generate some VO. And we want it to automatically generate the correct VO in order to give us the motor speed omega that we want. Now in order to do this, and in order to decide how to design this compensator here, or this feedback controller, we're going to break our system up into 3 different parts. And then we can connect these parts together at the end in order to generate the equation we want, relating Vref to omega. Now the first part we'll look at is from omega to Vs. So this is our speed sensor circuit, which takes omega to Vs. Next we'll look at our feedback controller, which takes the difference between Vref and Vs and generates a VO. And finally, we'll take a look at our motor driver and our motor and generate an equation which relates VO to omega. Once we have those 3 parts, that's the full loop. We'll model our motor driver and our motor to get a relation between VO and omega. We'll model our speed sensor to get a relation between omega and Vs. And then we'll generate a controller which will take Vref as an input and generate a necessary VO. So first of all, let's take a look at this speed sensor portion, which takes omega and generates Vs. And the goal here is to simplify the speed sensor circuitry, which includes a 555 timer, a low-pass filter, includes all these different elements. We'd like to simplify that down into some simple block. We want a transfer function that we can use to model this process of going from omega to Vs. So if we take a look back at how our speed sensor works, remember that we take some omega from our motor, and this is the physical speed of our motor, and the encoder generates some frequency encoder from that. We use this equation down here to relate the two. Our encoder frequency is the rotations of our motor over 2 pi times the number of encoder ticks per rotation, so 12, times our gearbox ratio. Now remember, depending on what type of motor you have, This might be 12 or it might be 13. But we have a relation between frequency encoder and omega, this first step here. Now our speed sensor circuit, our 555 based speed sensor, then takes that encoder frequency and generates some duty cycle based on our on time, which we solved for previously. Now we can relate this encoder frequency to the duty cycle or the on time with this equation down here, and that's after we've low passed it with our RC circuit. So now we have a relation between Vs and frequency encoder. And if we simply put these two equations together and solve for a relation between omega, which we want to be our input, and Vs, which we want to be our output, we can find that the transfer function for the speed sensor circuit is simply a constant k sense, which means that for any given motor speed omega, we know that Vs is simply equal to k sense times omega. And so we can use this equation right here in order to model our whole speed sensor circuit. So if we plug that back into our diagram, you'll see that it simplifies things quite a bit. Here we have omega coming out of our motor. We simply multiply by k sense. And so this node right here is going to be omega times k sense, which is equal to Vs. And so that's that portion of the loop. Next, let's take a look at how we use Vreference and Vsense to generate the correct VO. Now initially what we want to do is find out what's the error, what's the difference between where we are, which is Vs, and where we want to be, which is Vref. So we're simply going to subtract these two elements to generate some V error. And our V error is going to be equal to Vref minus Vs. And you can see this is a general way that we draw a summation block in one of these block diagrams. And we write the negative sign there to say that we're subtracting Vs, and the positive there to say we're adding Vref. So we now have an error voltage, V error, equal to the difference between these two. Then we want some function to act on that, which is going to generate the correct V out. Now what exactly goes into the block is pretty important here, because notice that what we want to do is have V error be 0. We want these two quantities to be the exact same. So our motor speed is the speed that we wanted it to be. And in order to do that, we're going to use an integral controller inside this block. The reason that we use an integrator is because we can have 0 input to our integrator and have a non-zero output. We want VO to not be 0 if we have 0 error, because that would mean our motor was stopped, and that's not what we want to do at all. So we're going to use an integrator in here, which allows us to have 0 input but non-zero output. And we're going to implement that using an op-amp circuit. So here's our implementation. We have our inputs Vref, our reference, and Vs, which is proportional to our speed, and our output VO. Now if we simply solve this circuit, we end up with the transfer function seen down here. And you can see here we have our V error, and here we have our VO. And so we have VO equals the integral, so 1 over s, of this error signal. And we have some parameter ki, which is going to determine how fast does this integrate. How fast is our error signal integrated in order to generate new VOs. Now if we place this back into our circuit, it gives us what we want. Here we have omega coming from our motor, multiplying by k sense to give us some Vs. Then we have Vs being compared to our V reference to generate some error signal and integrating that. And that whole comparison and integration happens in this feedback circuit here, or this feedback controller here, which generates a new V out. And this is our negative feedback circuit. This is how we're going to get the correct V out to give us the omega we want without having to manually adjust V out. It's just going to be based on the difference between Vs and V reference. So let's just take a look at how this works. If our sensed speed is too high, you can see that our error signal, if Vs is too high, so it's above reference, our error signal here is going to be negative. We're going to integrate this negative value and it's going to reduce VO. So VO is going to start to go down. When VO goes down, that's going to reduce the current coming through our motor. IDC is going down, which in turn slows down omega. And as omega slows down, our encoder frequency goes down, which reduces Vs. And this is just going to continue happening in this loop until Vs is equal to Vref. Error signal is 0, and VO has reached a new steady state. So let's take a little bit of a closer look about how some of these signals are going to react in this control loop. So here we have our reference voltage up top and our set voltage or our speed voltage Vs. And you can see that in steady state here we're just reached some steady state. These two quantities are equal to each other. If those are equal to each other, we have zero error voltage, so our error is 0. And at this operating point we have some omega or some motor speed, and to get that motor speed we're sitting at some VO, some control input to our motor driver. Now let's take a look at what happens if at this point in time everything's sitting constant. If we start going up a ramp with our robot, we've applied more torque to the wheels, it takes more power to go up that ramp, and so our motor speed has started to drop. And we don't want it to drop, we want to be at a constant speed. So what's going to happen here? Well, as omega starts to drop, Vs is going to start to drop as well. We know that Vs is simply a constant times omega from our model of our speed sensor. As Vs starts to drop, with our reference still held constant, our error is going to start to integrate up. So our error is going to go up as Vs drops. Because our error has gone up, our integral controller is going to start integrating VO, and VO is going to start to increase. It's going to increase as the integral of this error signal. As VO starts to increase, we're applying more current to our motor, so our motor speed starts to increase. Our motor speed starts to increase, so Vs starts to increase. As Vs starts to increase, V error starts to decrease. And as V error starts to decrease, VO, see V error is still a positive number, VO starts to increase slower, so it's slowing down, but it's still increasing, so omega is still going up. Omega goes up, so Vs goes up some more, Vs goes up some more, so V error goes down, and it continues in this process until omega has reached its reference value again. Vs is again equal to our reference Vref. Our error signal is again 0, and our VO has reached some new steady state operating point. And so now, in this whole region, we're now traveling up a ramp, but we're going the exact same speed as we were before. We've reached our steady state speed again. And you can see we now have 0 error, which is what we wanted. Vs is equal to Vref, which is what we wanted. But we now have a new steady state VO, so a new steady state control input to our motor driver. And this is fine because we don't really care what VO is, we simply care what omega is. So we had to increase VO because we required more torque to get up the ramp, but we're going the exact same speed, which is what we wanted. And so that's how this integral compensator is functioning. Now if we look back at our circuit diagram, we can replace this op-amp with the block diagram of our integral compensator. And that's everything inside here. We do this because it's a little bit easier to analyze. And you can see at the end, this VO right here, we get the exact expression that we would if we had the op-amp in here. Here we have Vref minus Vs times our Ki over S. And so this implements the exact same function as that op-amp, but it's much easier to analyze. Again, we have this block here which represents our sense circuitry. And now the only portion of this that we still need to simplify and come up with a model for is our motor driver and our motor. Now the first step to doing that is just recognizing what the inputs and outputs to this block are. You can see our input is this VO, this control voltage, and the output that we care about is omega, so the motor speed. So we can simply replace this whole motor driver and motor with a block which takes VO as an input and generates omega as an output, which we've done here. And now you can see this is much simpler and it'll be much easier to derive what we want finally, which is a relation between Vref and omega. Now what exactly goes inside of this block? Well, we can look back at our motor equations relating VDC of our motor to omega on the output, and we can derive a transfer function for our motor which relates VO to omega. And if we just do that, we end up with a transfer function seen here. We have a single pole on the bottom at some frequency determined by our motor parameters. We have some gain term out in front, and we'll simply call this transfer function GC of S, where GC of S relates omega to VO. So for any VO, we just do VO times GC of S equals our omega. And that's going to model our motor driver and our motor. And this was derived based off of our motor equations. There's some extra materials up on the lab website which will show you exactly how this was derived if you're curious. Now at this point we're in a good place to try attempting to write the equations relating Vref to omega. So let's try and do that now. Alright, we've just shrunk the circuit up to the top. It's the same circuit. We have GM modeling our controller. We have GC modeling our motor. We have K-sense modeling our sense circuitry. And so let's just begin writing equations. It's simple enough, we should be able to figure it out. Now if we start with just writing an equation for omega, we can see that omega equals whatever this voltage is times GM times GC. This voltage here is just Vref minus Vf, so we can see omega equals GM times GC times Vref minus Vs equals omega. So omega times, we have GC, we have GM, and then we have this difference here. Now we don't really want Vs in here because we don't care about Vs. So let's find Vs in terms of something we care about. And that's pretty easy to do. We'll see Vs, as we remember, is just K-sense times omega. So we can substitute that in. And now we have omega equals GM GC times Vref minus this K-sense times omega. And here we have an equation only in terms of known transfer functions and our input and our output. We have our output omega, we have our input Vref, and then we have the transfer functions that we derived. This one for our speed sensor circuit, this one for our motor, and this one for our integral compensator. Now we can simplify this a little bit. We can move omegas all over to the same side and just put this in terms of omega over Vref. And what we'll end up with is omega over Vref is equal to GCGM over 1 plus GCGM K-sense. And that's our final relation between omega and Vref. Now if we just define a quantity, we're going to find T. We'll just write it up here. We're going to find T equals K-sense times GM times GC. Then we can write this equation down here a little bit simpler. And that's going to be 1 over K-sense times T over 1 plus T. And that's our final equation for the relation between omega and Vref. Here we've just written them out a little bit clearer. Again, we have T equal to K cents times GC times GM, and this is traditionally called the loop gain. We call it the loop gain because if you picked a point on the loop and simply went all the way around once, you end up with this term, GM times GC times K cents. And so our full closed loop response to the system, GS, is going to equal this function here. Now our control parameter, the thing that we can change to vary exactly how this transfer function looks, is Ki. Now Ki is buried inside this TS because Ki is going to modify what GM looks like. But that's our control knob, so by varying Ki, we can change how this transfer function looks. And that'll be important for us. If Ki is too large, we can have some ringing on this transfer function, meaning that as we transition to a new omega, we overshoot the value we want and then we undershoot and we just ring back and forth until finally settling to our new steady state value. And if we have Ki too low, we're just going to take forever to get to the new omega that we want. So we'll design this closed loop system to give us the transfer function characteristics that we want. Now, just rewriting this whole circuit out, we still have one problem, which is we don't know how to change direction. Right now our motor is going to turn one direction. We have one of our control inputs, O2, is tied to ground, and we're simply varying this VO in order to get our motor to go between 0 speed and full speed in a single direction. So we're going to need to modify this a little bit in order to be able to change direction. Now, we're going to do that by driving this input here to 0 so that we can then vary this input. We want one of these at 0 at all time. So how are we going to drive this to 0? Well, we can do this just by fooling our integral compensator. And the way we do that is just think about if we tied Vs to 5 volts, what would happen? If Vs was 5 volts, then our compensator would see that V reference was lower than Vs, and it would think that our motor is going too fast. Because it thinks our motor is going too fast, it's going to reduce VO. Reducing VO is going to come around our feedback circuit, and it's going to try and reduce Vs, but we've tied Vs to 5 volts. So our compensator again is going to see that Vref is lower than Vs, and it's going to reduce VO further. And it's going to continue to reduce VO until VO hits 0 volts. Now when VO is at 0 volts, we can then simply apply the same integral compensator to the other side of our circuit to control our motor in the opposite direction. So we're just going to fool our integral compensator. We're going to tie Vs to 5 volts. Now we don't exactly want to just tie Vs to 5 volts because that's going to make our speed sensor unhappy. It's going to make one of its outputs tied to 5 volts, which can cause problems. So we're going to do this by inserting a switch on this node right here. And now you can see if we have a switch here, if we turn our switch on, then this is going to be tied to 5 volts, and this is going to be driven to 0. If we turn our switch off, this is going to follow Vs right here, and we're going to act as we want, which means that this is not true there. If our switch is open, this node is going to follow this node, and we'll get the feedback control that we want. If our switch is closed, this node is going to be tied to 5 volts, and this is going to be driven down to 0. Now we don't want to be just flipping a switch, we'd like this to be electrically controlled, so we're going to use a MOSFET in order to implement this. Now let's just take a look at how MOSFETs act before we try and put one in the circuit. There are two different types of MOSFETs, just like we have two different types of BJTs. We have an NMOS type and a PMOS device. MOSFETs are 3-terminal devices. They have a gate, a drain, and a source. And when we're drawing these, be very careful to include this little arrow on the inside, as that's going to tell us whether it's an NMOS or a PMOS type. Again, this is NMOS, this is PMOS. Just like with BJTs, the PMOS is the dual of the NMOS. Everything is simply reversed. And just like our BJTs, there's 3 different operating regions. The first region is cutoff. Now, in order for a MOSFET to do anything, VGS, so the voltage between the gate and the source, needs to be greater than what we call a threshold voltage. A threshold voltage will vary depending on what type of MOSFET you're using, but it's generally from below a volt to a couple volts. So if VGS is lower than our threshold, so this voltage is very small right here, our circuit's going to be cut off, meaning that it'll look like there's an open circuit between the drain and the source. We're going to have no current flow between drain and source. The same is true for a PMOS, except instead of VGS we have VSG, and for a PMOS the threshold voltage is a negative voltage, so we simply take the absolute value. But still a cutoff region where there's no current flow between drain and source. Our second region of operation is called the triode region. This is with VGS greater than a threshold, or VSG greater than a threshold. And remember, nothing can happen in a MOSFET unless our gate to source voltage is greater than a threshold. Additionally, for this operation region, we need our drain to source voltage to be less than VGS minus a threshold. If we operate here, the current from drain to source is going to vary depending on both VGS and on VDS. So depending on what voltage our drain is at and what voltage our gate is at, we're going to have different currents coming through the device. That's not really what we want. We don't want to have this voltage dependence on the current. We simply want it to act like an open switch. And so we're going to use MOSFETs in the cutoff region for a closed switch and in the saturation region for an open switch. Now in the saturation region, again, VGS is greater than a threshold, or VSG is greater than the absolute value of it. But in this case, VDS, or drain to source voltage, is larger than VGS minus V threshold. Now what this really means is that our source is at some low voltage. If we say this is our source voltage here, then we have our gate at some voltage which is slightly above our source, so the distance between these two voltages is greater than a threshold. And then our drain is at some voltage greater than both of these. So our drain is higher than our gate, and our gate is higher than our source. So this works, and this lets us operate in saturation, which looks like an open switch. It means that the current through is only really dependent on VGS. Apply enough VGS and you open the switch and it operates. Now PMOS acts fairly the same way, it's just everything is switched around. So we have VSG, this is a VSG, which determines the current through this switch. Now when we put this into the circuit, we're going to use a PMOS, and we'll see why that is in just a second. But in any case, we're going to operate in cutoff as an open switch, an open circuit, and saturation as a closed switch or a closed circuit, which is going to give us this voltage-dependent switch that we were looking for. So placing it in circuit, you can see here we have our PMOS with our drain tied here, our source tied here, and our gate tied here. Now if we pull our gate to 0 volts, that's going to put a large voltage. It's going to put 5 volts between gate and source, which is going to be much larger than the threshold for the device, and this circuit's going to turn on. So we're going to end up with a short there, which is going to stop our motor. Remember, if we short that, this goes to 5 volts. That fools our motor driver into driving this to 0 volts, which is what we wanted. Now if we raise this control signal up to 5 volts, that's going to put 0 volts between source and gate, which is going to turn the MOSFET off. It's going to turn the PMOS off. which is going to open this circuit, which is going to let our feedback loop act like it naturally would, which is going to regulate V out. So we put control to 0 in order to turn off this control loop. We put our control to 5 in order to turn on this control loop. Now I've used a PMOS here because we know that this voltage is going to stay at 5 volts, but that this voltage down here can range anywhere between 0 volts and 5 volts, meaning that our source to drain voltage can be anywhere from 0 to 5. If we used an NMOS, and you can look back at the operating region table back there, that this isn't going to work for an NMOS. We want to ensure that this device is either in cutoff or saturation. We don't want it to be in triode ever, because in triode we might have just a trickle of current coming through here depending on the drain to source voltage, and we really want this to either be tied to 5 or to be left open. So take a look at those operating region equations from the last slide, and you can see that a PMOS makes a lot of sense if we want this function. And so now that we can turn one side or the other off or on, we can simply take a look at the whole system as it works. Here we have one feedback controller for going this direction, and then we have our second feedback controller for going the other direction. So at any one time, only C1 or only C2 will be tied to 5 volts or tied to ground. These should be complementary signals. They should never be the same value. That's because we want to make sure that at all times either VO over here or this O2 over here, one of these needs to be grounded in order for the other one to interact. So when you build this, you'll actually be building 2 separate feedback controllers. You'll have 2 separate PMOSes to switch one of them on and off, and you'll use these C1 and C2 inputs to control the direction of your motor. Now we can use the same speed sensor output for both of these. So Vs is going to go into both of these feedback loops. And we can in fact use the same reference voltage for both sides here, because we'll simply vary the reference depending on what the magnitude of the speed is, and then we'll use C1 and C2 in order to determine the direction. So this is how we'll build it, and this is what it'll look like. If we go back to our full speed control system, you'll see here we have our control inputs, so one sends us clockwise and one sends us counterclockwise, and then we have our reference which determines the speed. Each of these two is going to drive one of those PMOSes in order to turn one side on or off, while our reference is going to be some between 0 and 5 volts to determine whether it's going 0 speed or full speed in whichever direction one of these switches has determined. We then have our 2 outputs. One of these outputs is from one or the other of the feedback controllers, and we connect that up to our motor driver, which we've already built. That drives the motor, which we've already characterized, and our omega is sensed by our speed sensor to generate this voltage proportional to the speed, which is then going back into our feedback circuit in order to keep the speed constant at whatever our reference speed was, regardless of extra torque on our motor. So that's how this whole system is going to work, and that's the final block that we need to analyze in order to have feedback control of our motor.